p in the valence cell. So you have a 1s and 3p. So to occupy all of the s and p orbital, you need 8 electrons because you have 4 electrons in 4 orbital in total. So when the atom gain or lose electrons, it will form ionic bonding. And when the atom share electrons, it will produce covalent bonding. And when we talk about the covalent bonding, we talk about the polarity. Okay. So one of the indicator to decide to predict the polarity of the chemical bond is electronegativity of the atom which bond each other. So if the difference in terms of electronegativity is higher, you could expect higher polarity for this chemical bond. So continue with the concept of using Lewis symbol. Now we move to the Lewis structure. So with the same idea on the paper, how we can, using the dot, represent electron to define what could be the most likely structure of this chemical compound. So we use the Lewis structure. So here are 5 rules you should remember, and when in practice you remember better. You should remember when you want to determine the Lewis structure of one chemical compound. First, you pick up the total valence electron from all the atoms make this molecule. Second, you write the symbol of the atom. So all the atom you will write out on the paper. The element with the less electronegativity is in the center, and then you put the remaining atoms surround this center, and you connect all of the atom with the central atom by a single bond. And you understand that one single bond is equal to 2 electrons. And then you complete the octets around all the atom bond to the center one. That means the atom surrounds. You put all the electron, valence electron you have to satisfy the octet rule. If after this action still have some electron left, you put in the central atom. If there are not enough electrons to give to the central atom and to make it satisfy the octet rule, you do the multiplication of the chemical bond. So basically, you start first with a single bond, and if the single bond is not correct, you change, you do the multiplication of the bond, starting from the double bond and then triple bond later. So with the 5 rules, let's say you make the Lewis structure of the molecule BCl3. So first, you do the total, you do the sum of the valence electrons. So the phosphorus in the column 5A, so you have 5 valence electrons. The chlorides, you have this element in the column 7A, so it will have a 7 valence electron. You have a 3 atom chlorides, so you have a 3 times 7, 21 electrons. So in total, the total valence electron for the PCl3 is 5 plus 3 times 7 equal to 26 electrons. Then, next step, you do the arrangement of the atom, because the phosphorus has lowest electronegativity, it has lower electronegativity compared with the chlorides. So you put the phosphorus in the center and 3 chlorides surround. And then you make a single bond between the chlorides and phosphorus in the center. So you have a 3 single bond as you see here. And then you complete the octet rule for the chlorides. So here you have 2 electron, 2 electron, and 2 electron, because here you have 2 electron already for the single bond. So in total here, the chloride you have 8 electron. The chloride here you have 8 electron. In this one you have 8 electron. So now what are the total electron you already used? 8 is so equal to 24 electron already. And because you have a total 26 electron, so you put 2 remain electron in the phosphorus. So now you look to see whether the phosphorus satisfies the octet rule. So you have 2 here, 2 here, and 2 here. So in total, the phosphorus also have 8 electrons. So you see that you use already all 26 electrons, and all the elements satisfy the rule of the octet rule. Okay, so we can stop here. So you have the final structure. So you can see that you have a final structure of the PCl3. Okay. So now, after having the Lewis structure of PCl3, the next question is quite interesting. Is PCl3 an acid Lewis or a Lewis base? What do you think? Is an acid or a base?
I have a question first.
Yeah,
please.
Yep,
How can we determine whether a compound is acid or base?
Okay, thank you for this question. Anyone can help to answer the question from your classmates?
So maybe if it donates proton, then it would be an acid, and if it takes a proton, then it would be a base.
Okay, thank you. Any other comment?
I think
It can be about the electron. Can you keep going?
Okay, so I think it depends on the charge of the compound. If the charge is negative, so it is an acid. If it's positive, it's a base.
Okay, so basically you have different definition of the acids and base. So now if we look at the Lewis acid or Lewis base, that means the acids base definition by Lewis. So one compound that can give electron is a base. Okay, and one compound which accept electron is acid. Okay, so at the high school you have a definition of acids with acids that can provide S plus, and base that can provide OS minus, right? So it's also accept S plus. Is it correct?
Yes.
Yes.
So you can see here is a little bit larger, the Lewis definition. So one compound that can give electron, so that means it have accept electron, EB1. So it have accept electron, that means in the atom center you have negative charge. So that can be accept the proton. Sorry, it should be here. It can accept the proton. Okay, so it's quite similar in some sense, but what could be the difference? Let's say by using the concept of acid-base classic, you cannot define whether nickel 2 plus is acid or base. But by using the Lewis definition, you can define whether nickel 2 plus is acid or base. Because if you apply the concept of the acids, like acids can provide S plus, so nickel 2 plus cannot provide S plus, so it's not acid. But if you say that nickel can accept electron and become acid, then nickel is one acid because it accepts electron. You get what I mean?
Yep.
Yes.
So by this definition, whether BCl3 is an acid or a base. In your opinion, what's your opinion?
So I think PCl3 will be a base.
Yes. So basically here you have a pair of electrons on the phosphorus, so it can give the electron, so it become a Lewis base. And I mentioned that nickel 2 plus is a Lewis acid. So basically you have the reaction acid plus base provide source, right? S plus plus OH minus provide H2O. Huh? So here you have a Lewis acid, which is nickel 2 plus. Here you have a Lewis base. So basically you have this product of the acid by reaction. You can imagine like a source. But later when you learn inorganic chemistry, it's a complex with a coordination bond. Okay? So to conclude, if you have the central atom which have except electron, that means a pair of electron, non-pair, non-bonding, sorry, non-bonding pair electron. So that means the non-bonding pair of electron can give. So it's become a Lewis base. Okay?
Professor,
Yep.
I have another question.
Please.
Why doesn't the compound give electron pairs from the chlorine atoms?
Because the rules when you draw out the Lewis structure is that you put the lowest electronegativity in the center and the higher electronegativity atom outside. So basically, in terms of electronegativity of chlorides is higher than the electronegativity of phosphorus, right? So basically, the chlorides will have a tendency to keep electron stronger than for the case of phosphorus. You understand what I mean?
Yes, thank you.
Yeah. Thank you. So now, can you do okay practice? Can you draw out the Lewis structure of NO2? Can you pick up your paper and draw the structure of NO2 by 5 steps that you have here? Can you try? Anyone has finished? Hello, hello. Anyone has finished?
I do this.
Yes. Can you share can you pick up a photo and you share to all of the class to show how you can do? I stop
Okay.
sharing. Yes.
Wait me a minute.
Okay.
I send my picture.
Yes, please.
I already sent it.
Can you share or how did you do?
So nitrogen is the element with lower electronegativity. So I put it in the central,
Mm.
and And then I make the single bond with the 2 oxygens. And well, since like one, so may I speak in Vietnamese for?
Okay, try in English, please.
So first, I draw the Lewis structure of NO, and then on nitrogen there will be left one single electron and then one pair of electron, and I just like give the electron pair to oxygens to the other oxygens.
Okay. Okay, thank you, Vu. So you can do for like you have 5 steps, right? So the first one you have molecule. Can you see my screen?
Yes, teacher.
Oh, wait.
Okay, so molecule NO2, right? So now we calculate the total number of valence electrons. So the nitrogen, you have 5, oxygen, you have 6. So in total molecule NO2, you have 6 times 2 plus 5, sorry, equal to 17 electron, valence electron. Okay, and you see that nitrogen have no electronegativity, so you have put the nitrogen in the center. You have, if you want, you can put like this, like oxygen like this one, right? The nitrogen is the center because it have no electronegativity. And then the next step, you make a single bond from the oxygen to nitrogen, and then you try to put the 7 electron to satisfy first the octet rule of outer atom, which is oxygen. So you have a pair of electron here, a pair of electron here, a pair of electron here, because here you have a pair. So here you have 8 electrons. Here you have a pair of electrons, so you put like this. So in total you have 8 electrons as well. Now, in this case, the molecule will have 8 plus 8 electron equal to 16 electron already. And you have a total 17 electrons, so you put the left over electron in the nitrogen, so you have this one. Now you look at the number of electrons surround the nitrogen. So you have 2 electrons, so in total here, you have 2 plus 2 plus 1 equal to 5 electrons, very small compared with the electron you need to satisfy the octet rule, okay? So in this case, the suggestion is you try to change the structure by doing the multi-bond between the oxygen and nitrogen. So you do the same thing, nitrogen, oxygen, and then instead of using the single bond, you use the double bond, okay? And then the second one you less is single bond. Then you also doing the completion of the octet rule for oxygen. So here you still have 6 electrons, but here you have already 4 electrons for the double bond. So you need only 4 electrons to complete the octet electron of the oxygen. So here now in total for oxygen here, you have 8 electrons. This oxygen, you have 8 electrons. And then in total, you still have a 16 electron. So you put the 17th electron here. Now about the nitrogen, you will have the total number of electrons equal to 4 plus 1 plus 2 equal to 7 electrons, closer to 8 electrons compared with the 5 electrons you have in the first solution. Now, if I do the same thing, but I try to do the multiplication with oxygen like this, okay? So I will have 4 electrons here, 4 electrons here. So in total, I still have 8 electrons, 8 electrons, and I have 1 electron here. How about the nitrogen here? So the nitrogen now, you will have 4 plus 4 plus 1 equal to 9 electrons. So it's larger than 8 electrons. So basically, the most likely structure would be the second solution, this one. Is it clear?
Yes.
Yes? Okay, thank you. Now, another exercise for you guys, because it's something you should practice, you should do by yourself, otherwise it's quite complicated to remember. It's not very difficult, but you need to practice. So now, can you write down the Lewis structure, draw the Lewis structure of the B bromide, BrO3 minus ion? This one. Can you? Can you try in about 3 minutes? Like imagine that we are in the final exam. Have you finished? Anyone can share your work? Hello. Vũ?
Okay. May I draw on your slide? I will
Yes,
delete
yes,
the draw later. Okay.
yes.
So wait me a bit. Can you see my drawing?
Yes.
Yes. So I think bromine will be the central, and like this. There will be 2 electrons here. For on the electrons with double bond, and 6 on the electron with single bond.
Mm-hmm.
There is my Lewis structure for BrO3 minus.
Okay, so let's say you will have 6, 8, 8, 4. But in this case, you have here the bromide in the center. The center bromide will have 4 plus 4 plus 2, right? It will
Yes.
have it will have 10 electrons. Is it correct? It's too much.
Yes. Yes, I think I should erase the 2 electron here, the pair.
But
I think so.
even you erase 2 electrons here there, it will have still 4, 4, 4, and here you have 2. So in total, you still have 10 electrons.
But I think it still be okay because I think brom it will have like the outer shell of D and F, so it can like satisfy the 18 electron. I think so.
Well, let's consider the case following. Let's say you have the bromide is 7 electrons, right? Oxygen, it will have 6 electrons. So BrO3, it will have 7 plus 3 times 6. And then because it's minus, so you plus 1 equal to 18 plus 8 equal to 24. Is it correct? Now you put bromide, you
It's
put
26.
oxygen. Sorry?
It's 26.
Oh, sorry. Sorry for that. Okay. So you have oxygen, okay? So now if you put the 2 electron here, Huh? So you have here you have 8 electron. Here you have 8 electron. Here you have 8 electron. Okay, and in total you have already 24 electron. So because you need 26, so you put 2 electron here. So in that case, you will have bromide or also satisfy 8 electrons. So it should be okay for the moment. Is it correct?
Yes, I think so.
So the correct structure should be the structure that I propose here. Okay.
Yes, okay.
Thank you. So I invite you guys at home, you try to pick up any structure in the lecture note or in the exercise that your professor who work with you in the tutorial class send to you, and then try to practice yourself, okay? Now, when there are more than one way to draw the language structure, how can we decide which way is correct? To decide which way is correct, we must use what we call the formal chart. For example, here you see 3 language structure. It seems satisfy the octet rule. So which one of the 3 language structure is most likely? So to decide, we use the formal chart. So you ask question, what could be the formal chart? The definition, the formal chart, that is the chart one atom would have if all the atoms in the molecule have the same electron negativity. Each bonding electron pair in the molecule will share equally between the 2 atoms. Let's say, if you pick up the structure you see here, the carbon-nitrogen triple bond, okay? You know very well that the nitrogen have like a higher electronegativity compared with the carbon. But now to calculate the formal chart, you imagine that the carbon and nitrogen have the same electronegativity. And when they have the same electronegativity, that means the covalent bond between them will be nonpolar. And by definition of the nonpolar covalent bond, that means the electron density will equally distribute for the 2 atoms. So it says that if you have 2 electrons of one valent bond, you can imagine each atom will pick up 1. Okay? So let's apply this kind of idea in this bonding. So the molecule Cl, the C triple bond nitrogen. So here in total, you have 6 electrons. Okay. Normally, 6 electrons will more localized with higher electron density to the nitrogen and less lower electron density to the carbon, because nitrogen have a higher electronegativity. However, when we calculate the formal chart, we assume that the carbon and nitrogen have a same electronegativity. So you pick up 6 electrons of this triple bond, you divide by 2. So 3 electrons will be on the nitrogen and 3 electrons will be on the carbon. So now in total, how many electron nitrogen will have? It have 3 electrons plus 2 electrons non-bonding pair here. So in total, you have 5 electrons. And because nitrogens have the 5 valent electron, normal before the bonding is have 5 valent electron. So in this bonding, you can imagine that it's exactly 5 valent electron is have before. So the net formal charge on the nitrogen will be 0. How about the carbon? The total number of carbon will be 3 electrons here plus 2 electrons, so it will have 5 electrons. But because carbon have only 4 valent electrons, now in this bonding, it have 5 electrons belong to it. So it means that it have 1 electron excess compared with before bonding. So the former charge would be -1, representing for 1 electron excess. Is it clear for you guys how we can calculate the former charge?
Yes.
Yes or not?
Yep.
Okay, thank you. Now, let's recalculate the former charge for this 3 structure. So the nitrogen here, you have 2. So you pick up divide. So you have 2, 4, 6, 7. So -2. And the carbon here, you have 1 and you have 3. That means 4. That means the former charge will be 0. And 3 plus 2 equal to 5. The sulfur have a 6 valent electron. In the bonding, you have only 5 electrons belong to the sulfur. That means it lack 1 electron. So the formal charge will be 1. For the second compound, you divide by 2 like this. So here you have 2 electrons. In total, the nitrogen will have 6 electrons. It will have a formal charge -1. The carbon will have a 4 electrons. So it's a formal charge 0. The sulfur will have 2, 4, and 2 electrons here. In total, you have 6 electrons, so the formal charge will be 0. Now, for the third compound, you have 3 electrons here. So in total, you have 5 electrons for the nitrogen. So the formal charge for the nitrogen will be 0. The carbon will have 4 electrons because it's like this. So in total, you have formal charge 0. And the sulfur, it will have 6 plus 1, 7. So you have -1 like a formal charge. Okay, so we already calculate the formal charge of all the atoms in the 3 chemical structure, Lewis structure. So to choose the correct structure, we base on 2 rules. First, we generally choose the Lewis structure in which the atom bear formal charge closest to 0. Okay, and the second, we generally choose the Lewis structure in which any negative charge resides on the more electron negative atom. Let's we base on the first one. We choose the Lewis structure in which the atom bear formal charge closest to 0. So here you have 2 in the central structure. You have 2 atoms bear the formal charge 0 and 1 -1. The second one, also you have 2 atoms with a formal charge 0 and 1 with a formal charge -1. So the 2 structures are quite equal. How about the first structure? The formal charge of the nitrogen is -2, carbon 0, and the sulfur +1. That means this quite is far from 0 compared with the 2 others. So the structure, when we apply the first rule, this structure, the first structure is not acceptable because the nitrogen have -2 formal charge is far from 0 compared with -1 in the 2 other structure. Is it clear?
Clear.
Then we move to the second one. We generally choose the Lewis structure in which any negative charge will reside on the more electron negative atom. So basically, the 2 structure, second and third, they have equal formal charge, -1 localized on the nitrogen in the second one, and -1 localized on the sulfur in the third structure. Which one is more likely? It's more likely when we base on the second rule, the negative charge will push on the more electronegative atom. So now we need to compare the electronegativity of the nitrogen and sulfur. So if you pick up this Can you see the data here? So you see that the nitrogen will have an electronegativity of 3 plus, and the sulfur will have an electronegativity of 2.5. So that means the nitrogen is more negative electronegativity compared with the sulfur. So when we are back, we can see that the negative charge is more likely localized on the nitrogen rather on the sulfur. So the correct answer would be the second structure. Is it clear?
Yes.
More or less.
Okay.
Okay. So by using, first you should remember the way you do the calculation for the formal charge. Remember that the formal charge is not the real charge of the atom. It's just a way to decide which structure is correct. So you should remember the way you do the calculation for the formal charge, and then you remember on the two rules for deciding which one is more likely. First, we choose a Lewis structure in which the atom be a formal charge closer to 0. Second, when you have a negative charge on one atom, then it's better is you put the negative charge on the atom which have higher electronegativity. Okay. Now, when you have, let's we look at the two structure, Lewis structure of O3, ozone. Okay, we talk about the resonance structure. So when you look at the structure of the ozone, O3, you will see that both the structure 1 and the structure 2 will satisfy the Lewis structure. It satisfies the octet rule upon the atom. Now, if you look at the first structure, you can see that you have one oxygen in the center and two atoms outside. Let's put the atom A, B, and C. If you just look in the structure 1, you see that the bonding distance between A and B will be shorter than the bonding distance between the B and C, right? Because AB, you have a double bond, so it's softer and stronger compared with the BC, you have a single bond, which should be longer and weaker. Now, if you do the acid-base reaction, for example, you have S plus, where the proton can attack. So basically, you can expect that the oxygen C will have highest basicity, right? It means you have a higher electron density. So the proton can attack here. You can see by considering about the structure parameter and considering about the chemical behavior, you can say that the oxygen A totally different compared with oxygen C. You also say you wouldn't have an ability to distinguish A and C because they are different. But experimentally, when you put the proton in this compound, you cannot distinguish A and C. And when you do the measurement of the structure, you cannot distinguish you will see the identical bond distance between oxygen A, B, and oxygen B, C. That means in reality, you will not have this, but you have DAB equal to DBC. That means A and C are identical. So we develop theory in the chemistry, not for fun, not to satisfy our imagination, but we develop the theory, we develop our imagination to explain experimentation, explain experimental result. So the truth is on the experimental result, not on our imagination. So when we have experimental result, which is different compared with our imagination, we need to adapt. We need to revise our imagination to explain better the experimental result. So how we can explain the experimental result? Here is as we say between both the structure 1 and 2 are correct and they are resonant. That means it can move from 1 to 2, 2 to 1. And both 1 and 2 exist in one equilibrium. And normally you cannot distinguish because both exist. You get what I mean? So what I explained to you is why we imagine and we develop the theory of resonance structure. Resonance structure is not something you imagine for fun. You imagine not just for imagination. You imagine because the Lewis structure have some difficulty to explain fully the experimentation. Take the case of O3 molecule. The Lewis structure say that in 3 oxygen, the oxygen A and C will be different and you can distinguish it experimentally. However, in the real experimentation, you cannot distinguish A and C. And the bond length between the A, B, and BC are exactly equal. So to explain this, we say that structure 1 and structure 2 are both exist and they are resonant. That means they can change from 1 to 2, 2 to 1 spontaneously. So that is the motivation to develop the concept of resonance structure. So resonance structure are used when 2 or more equal valid Lewis structure can be written and they coexist. Is it clear?
Yes.
Okay. So here you can see that experimentally, the bond distance between O A here and O B C here, the bond O A O B equal to O B O C. So basically, experimentally, you cannot distinguish. So that's the reason the structure 1 and structure 2 are in resonance. Okay. Now we discussed quite a lot about the octet rule. When we talk about the chemistry, we talk about the exception. So what could be the exception of the octet rule? Exception, there are 3 main types of exception. First, the odd number of electrons. So when you have an odd number of electrons, you cannot satisfy the octet rule because the octet rule is an even number. When you have fewer than an octet of the valence electron, and when you have a more than an octet of a valence electron. So we will go one by one in this case. So for the case of NO, right? So NO, you have 1 nitrogen with 5 electrons and 1 oxygen with 6 electrons. So you have 11 valence electrons. So it's an odd number. So of course, if nitrogen can satisfy the octet rule, then oxygen cannot. If oxygen satisfies the octet rule, then the nitrogen cannot. Okay, so the same for the molecule NO2 that we just described, because nitrogen have 5, oxygen have 6, so in total you have 17 electrons. So of course, the nitrogen will not satisfy the octet rule, is have an odd number. Second exception, you have fewer than an octet. That means you have a less than 8 electrons. Take the case of BF3. So BF3, you have in total 24 electrons. So the correct answer for the octet, for the Lewis structure is this one. And then you will see that the boron here, you have thus 6 electrons, smaller than 8 electrons. Okay? So in this case, what will happen? You have a boron have a lower number of the valence electron compared with the octet rule. So it will have tendency to receive electron. When it's receive electron, that means it will react at a Lewis acid. So that's why it's BF3 strongly react with ammonia, because ammonia is one Lewis base. So you have it's become a Lewis acid. So you see that a base and a 3 react with an acid BF3 to make a compound which is a source acid base. So in this case, you have the boron now is satisfying 8 electron thanks to this acid base reaction. Now that we talk about the fewer than octet, how about more than an octet? So when you have the element in the third barriers or boson, that means in the third and fourth barriers of the periodic table of element, when the element have orbital d, and when it have orbital d, we discussed in the previous lecture that the element can satisfy the total number of maximum total number of electrons is 18 because you have 1s, 3b, and 5d. So in total you have 9 orbital. So you can accumulate, you can accept 18 electrons instead of only octet, that means 8 electrons. So in that case, you can make chemical compound with the central atom, which from the third barriers, fourth barriers, and so on, which have more than 8 electrons. So in the case of, for example, the BCl5 here, so you have phosphorus 5 times 2 equal to 10 electrons, is larger than 8 electrons. And the sulfur here, you have 6 times 2 equal to 12 electrons, is higher than 8 electrons. Okay? So, but it's only acceptable for the element which have a d orbital. So when you talk about the first row and second row, it's not acceptable to have more than 8 electrons. Oof. Okay. Here's something I would like to, because we talk about exception. I already shared with you few exceptions that's already written in the textbook. First, about the odd number of electrons. Second, fewer than octet. Third, more than an octet. There are 3 common exceptions that you have learned because they are written in the textbook. Some exceptions are being developed in the literature, in the research now, and have not yet written in any textbook, but I would like to inform to you about the exception. So when you learn organic chemistry, you start with the compound of CH4. So you have 4 bonding like this, right? Why the 4 bonding? Because the carbon is in the 4A group, which have 4 valent electrons. So with 4 valent electrons, you can imagine that you have S and B like this. So we have 1, 2, 3, 4 electrons. So X, you can make 1 chemical bonding because you have 4 single electron like this. Because the idea is when you share electron, you bring 1 electron from you guys to share with another one. So you have a 4 electron, you can share with maximum 4 other guys to make 4 sigma bond, and the model you can see is in the compound CH4. Of course, you can see also that you can make a structure with a double bond like this, and you can make a structure with triple bond. Okay, but anyway, your professor will say that the maximum sigma bond that the carbon can produce is 4. And you can make 1 3 sigma bond and 1 p bond, 2 sigma bond and 2 p bond. Right? In total, you cannot make more than 4 bonds. That is in the textbook, right? However, very recently, few years ago, a research group in Germany, they published this structure. You can see that the carbon now can access 4 bond limit. So the black here is carbon. Carbon, 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 carbon. And here you have carbon. So you see that the carbon atom here, it will have 1, 2, 3, 4, 5, 6. So this carbon have 6 sigma bond. It's higher than 4 sigma bond. Thus, you can imagine. Okay? And this is not a drawing or an imagination. It's a crystal structure. That means this compound has been isolated, crystallized to get a single crystal, and this structure has been evident by single crystal X-ray diffraction in the lab. They published in early of 2017. You see, one beautiful exception, and it shows how complicated chemistry would be. So I don't know what could be the next textbook in organic chemistry, or how we can describe the chemical bonding more precise. How can we develop the theory of bonding to explain this experimentation? You get what I mean? Anyone in this class can imagine how with 4 electrons in the valence cell, the carbon can generate 6 sigma bond totally equal. Anyone can imagine how we can do this? So this compound has been made by a chemical reaction. When you take this compound and then you reduce in a strong acidic environment. So you have this single crystal, they isolate it and do the crystallization. So take it easy, I just share with you this exam to tell you that exception in the chemistry is ongoing and continue to be reproduced in the research, and very likely that you guys, the next generation of chemists or technology, you should think about, you should imagine more about the future theory of the chemical bonding. Okay, so the chemical bonding we are discussing now in the class of general chemistry is not something fixed and already done, cannot develop more. It's fixed, it's already in the textbook because it's well explained all the experimentation discovered before. But now with the new experimentation, new coming, so we need to imagine more and we need to develop more, and hope that you guys, some of you, will be interested with this chemistry and contribute for the international combination, international community in the future. Okay, now we talk about the strength and length of the covalent bond. We talked already about the polarity. So now to describe about the strength of the covalent bond, we talk about the bond enthalpy. The enthalpy change and the age for the breaking of a particle bond in 1 mole of a gaseous substance. So you see that when we define the ionization energy, the bonding energy, we define on the basis of 1 mole of gaseous compound. That means we do all the physical state transformation from the solid, from the liquid to the gas. And then we make the calculation in the gas phase. Okay, so the bond enthalpy is the enthalpy change for the breaking. That means the energy you need to put inside to cut a particle bond in 1 mole of gaseous substance. So if you are given a compound which is not yet in the gas phase, you need to calculate the energy to transfer from the solid or liquid phase to the gas. And then from the gas phase, you cut it. So you have the bond enthalpy. For diatomic molecule, that means a molecule with the 2 atoms, they are accurately measured in quantity. For example, you take the molecule of chloride, you cut it into 2 atoms of chloride in the gas phase. So you have the enthalpy of the single bond you see here. You can have also the enthalpy of double bond or triple bond. With the same concept, you take 1 mole of the gas, and then you put energy to cut it in 2 mole of gas atom. Then you have the bond enthalpy, which is equal to the amount of energy. So you see that the delta H, the bond enthalpy, always have a positive value because that represents the energy input, the energy you need to put inside the system to break the chemical bonding. It also means when you form, when you generate the chemical bond, it will generate energy. So the chunk of covalent bond when we have multi bond. So average bond enthalpy are used for polyatomic molecule. For example, when you take the molecule CH4, you have 1 carbon and 4 hydrogen. So you understand that for bonding between carbon and hydrogen are equal. So instead of measuring X enthalpy of X bond, we say that for chemical bond CH, we have the same enthalpy. So you take the energy breaking for molecule CH4 in the gas to 1 molecule, 1 mole of the carbon gas and 4 mole of hydrogen gas. You have enthalpy of this reaction. So the bond enthalpy will be the average of this reaction divided by 4 because you have 4 CH identical. So you have the bond enthalpy is 415 kilojoule per mole. A molecule with strong chemical bond generally have less tendency to undergo chemical change than does one with a weak bond. So we say stronger chemical bond mean more stable. More stable means less reactive in the chemical reaction. And you have weaker bonding, so that means the molecule is less stable. Is less stable, it also means more reactive. So it's have a more tendency to react in a chemical reaction. Okay, so you can say that the single bond is easier to be cut, so it's more. It's less stable, it's more reactive than a double bond, and the double bond is more active than a triple bond. Now, we finish with the enthalpy of reaction. So basically, you have a reactant. So by the definition, the bond enthalpy is the energy you put inside to cast on the chemical bond to make the atom a single atom. And when the single atom combine to make a new compound, which are products, so you will see that the energy will decrease. I recall you again, is that's when you put in the potential energy. You start from reaction. You go 1 cycle from reaction to the single atom to the product and go back to the reaction. The delta E of the cycle will equal to 0. Because you start from 1 point, you go 1 cycle, you go back in exactly the same position. So the delta E cycle will be equal to 0. So imagine that here from the reaction to the product, you have enthalpy of reaction. Yeah, or you can say reaction. Okay, so how can we calculate the enthalpy of reaction? If you know the enthalpy of reaction and enthalpy of the product. So here you have enthalpy of reactant. Okay, here you have enthalpy of the reactant, and here you have enthalpy of the product. Okay, so if you take like one cycle equal to 0, that means you have delta H reaction plus delta S a product minus delta S a reactant. That means the inverse will be equal to 0. Okay, so from that you can have this equation where the delta S of reaction equal to the delta E of reactant minus delta S of the product. Can you see it? So the idea is that when you start from one position, you go in one cycle, you will have exactly the same potential energy. So that means delta S equal to 0. So you do this equation, you have this result. Is it clear for you guys?
Yes.
Okay. Now, so how can we calculate the enthalpy of reaction? For example, if you consider this reaction, CH4 plus chloride. So here you have CH4 plus Cl2. You have CH3Cl plus HCl. Okay. So reactant broken bond of 1 mole, you need to have to calculate the delta H of this one. You know this equation, right? Bond enthalpy of reactant minus bond enthalpy of product. So first, you need to identify what are the product and what are the reactant. So the product, you have HCl here. You have 2 kind product, carbon chloride, hydrogen chloride, they are product. So you need to know the enthalpy of the chemical bonding. And the reactant, you break the carbon of the chloride, so you need to know the enthalpy of this one and also the enthalpy of carbon hydrogen. From that, you can calculate the enthalpy of the reaction. So basically, the enthalpy of reaction would be the enthalpy of the reactant. That means carbon hydrogen, enthalpy of second reactant chloride, and minus the enthalpy of the product, carbon chloride here, enthalpy of the hydrogen chloride here. So you put inside the value, you will have this equation, and the final result will be minus 104 kilojoule per mole if you want. So because the energy have a negative value, so the reaction could be exothermic or endothermic. What do you think? Is it reaction exothermic or endothermic?
It's exothermic.
Okay, so because it's negative in charge, negative value, so it's exothermic. It means that when the reaction happens, it will really heat. Okay. So let's practice a little bit. Can you calculate the enthalpy of direction for the following reaction? CS4 plus bromide. Can you try to calculate if you are given this table? Anyone got the result?
This may not be correct that I got negative.
Sorry?
Oh, I'm sorry. I got negative 36 kilojoules per mole.
36, okay.
Negative
Okay.
36.
Anyone got other result? Hmm? Let's wait for about 2 more minutes to see anyone have other result or not. What is your result? Hmm?
I also get negative 36.
Okay.
You choose.
Nguyễn Tiến Nam, what is your result?
No, I don't calculate.
You don't calculate.
Kiểu chưa xong ấy thầy ạ, chứ không phải.
Okay.
Minus 36.
Minus 36. Okay, let we see. Phạm Hà Châu. Châu? No. David, what's your result?
I don't have a result yet.
Really?
Yeah.
Nguyễn Ngọc Khôi.
Yes, teacher.
Nguyễn Nhật Minh.
I don't have the results yet.
But you are trying to calculate or not?
Yes, I'm calculating.
Đỗ Diệu Anh. Trần Đức Tuấn. No? Okay. If you have minus 36, can you show us how you get this result? How you did the calculation? Okay. So basically, here you have the reaction quite similar. You have CA3 8 plus ER provide CA3 ER plus SER. Okay. So you need to know first the bonding, the enthalpy of C8. This one. So this. The bromide is this one. That's for reaction. So the delta S equal to delta S of reactant minus delta S of the product. Alright. So first you know about the reaction. Here you have the carbon bromide. So the carbon bromide is here. You have S bromide, so A bromide will be here. Okay. So first you have reactant is equal to 1 minus 1 plus 1 3 minus carbon bromide 276 plus 366, right? Is it correct?
Yes.
So you will have 6 0 6 minus 6
642.
sorry, is it correct?
Yes.
So it's minus 36 kilojoule per mole, as you mentioned. So for all of you, is it understandable?
Yes.
Okay. So when you are asked, you don't need to remember, you just need to understand the way you do the calculation. You do not need to remember this data because of course nobody can remember. So if you are asked in the midterm or in the final test to calculate this kind of enthalpy, so you are given this table, okay? The problem is just how you understand the calculation and which value you pick up, okay? So in terms of the covalent bond length, so the distance, the bond length, you see that the single bond is longer than the double bond and much longer than the triple bond. And in the inverse, in terms of the bond strength, you will understand that the single bond is weaker than the double bond and which is weaker than the triple bond. So we can understand as the number of bonds between the two atoms increase, the bond grows faster and gets stronger. And when it gets stronger, it also means it's become less active. So if you have a triple bond, you want to cut it will be much more difficult compared with a double bond and a single bond. Okay. So here is table show you how the bond length evaluates when you move from the single bond to the double bond. You have the same chain when you have a single bond is longer than the double bond and so on. So it's quite easy to understand, not need to focus more. So to conclude, we have discussion in this lecture, the drawing of language structure, a few messages. You need to put the less electronegativity element in the middle, and to choose the correct one, you need to know how calculate the formal charge, and you have two rules to decide which one is which language structure is more likely based on the formal charge. Closer to the zero is better. And when you have a negative charge, it's better to put a formal negative charge in the element which have a higher electronegativity. And we talk about the resonance structure. We use the resonance structure when you have a two or more than two language structure that can be written and that can be exactly identical. When we say that they are identical, it also means in the experimentation, in the experiment, we cannot distinguish the structure. So that means they are exactly equal. You have some exception of the octet rule. You can have language structure which is stable. Even the central atom is not satisfying the octet rule because it has odd number of electrons. It can have also less than 8 electrons. That means it's not satisfying, obey the octet rule. It can have more than 8 electrons. In the case of more than 8 electrons, normally the atom will be in the third row or below. That means third row, fourth row, and fifth row of the periodic table of element. Because in that case, the atom will have a d orbital, and when you have a d orbital, instead of satisfying the octet rule 8 electron, you can calculate, you can accumulate until 18 electrons because you have 1 orbital s, 3 orbital b, and 5 orbital d. And we know how to calculate about the bond enthalpy, one chemical bond, and also based on the bond enthalpy of the reactant and the bond enthalpy of the product, how can we calculate the enthalpy of the chemical reaction? And based on that, you can understand whether the reaction is exothermic or endothermic. When you move from the single bond to the double bond and triple bond, you get shorter bond length, but also stronger in terms of the bond strength, and also it's become less active. Okay, so that's all for the moment. That's all for this lecture. So in the next week's lecture, we will start to discuss about the geometry of the molecule, and also we move to a topic which is extremely important, which is the molecular orbital theory. Okay, so I think that I can end my lecture today now. Do you have any question? We can discuss. Otherwise, we can wait for the next lecture in the next week. Do you have any question?
Can I have a question?
Yeah, please.
So, for example, in the CH4 molecular, when we substitute heros atom by the, for example, chlorous atom, is the enthalpy of the CH in these two molecular?
You mean that's the bonding of CS between inside the CH4 and inside the CH3Cl? You mean that, right?
Yes.
But basically, we consider they have the same value. Okay.
Yeah. Okay. Thank you.
Because actually, that's very good question. Actually, it can be difficult or different, but to clarify whether it's different or not, we need to do the experimentation. We need to do the experimental measurement. But we cannot, the number of the chemical compound is a huge number, right? You have CH4, CH3Cl, CH3 Br, CH3 iodide, you have CH2 chloride, and so on. You see, the total number of compound is a huge number. So we cannot establish the measurement for X compound to identify the enthalpy for X chemical bond in X chemical compound. You get what I mean? It will be not realistic. So we assume that the bond strength of the CH inside the CH4 and CH3Cl will be identical. Even we understand that when you move from CH4 to CH3Cl, the polarity of the compound will be different. So the reactivity of the CS will be different. And of course, we can expect a change in terms of enthalpy. But for the moment, to keep it simple and accessible for all, we consider that CS strength in the CH4 or CH3Cl will be identical, similar. Okay?
Yeah, okay, thank you.
Other question? Okay. If not, thank you for attending this lecture, and I wish you very nice end year holiday if you have. I guess 1 or 2 days off, and then enjoy the holiday to recharge your energy, to make you ready for the last lecture and prepare well for the final exam that will become after the date, right? You will have all the final exam after this holiday. So I can say Happy New Year, enjoy and take care, okay?
Thank you.
Thank you,
Professor.
bye-bye.
Yeah.
Happy New Year, teacher.
Welcome,
Bye-bye.
Professor.